All right, so for the last two examples in our notes, we're back to those two-column proofs, which I know you all love. So we need to make sure that, and I've kind of taught this from day one, but when you start a proof, you really want to look at your givens and say, what can I write or put on the diagram, mark it. Well, it's kind of hard in this one because it's saying that J, so I am going to mark this kind of along with the given, but if you look in the proof, if we pre-look ahead, what you should do is separate them. So J, I don't want congruent symbols, so I'm going to mark J, and then I'm going to start with K, and let's only focus on those two first. Now they're supplementary. Now these are not the markings for supplementary, but I know that these two things add to 180 degrees when I add them up. So kind of funky, but that might just kind of help you see what's going on. Now, even without knowing what our reasons are, our goal is to prove that this is a parallelogram. We do not know that. So all of those properties and things and theorems that you learned today on the front, we know none of that because all we know is that this is a four-sided figure. So they told us that J and K are supplementary. Now, even without filling in step 2, I think you can probably understand that JM, just by kind of common sense, is going to be parallel to what? Well, I'm hoping you say KL. Now, this is the part that I really need to guide you with. Because why is it that we can suddenly say, just from this information of supplementary angles, of consecutive there, that these are parallel? So what I'm going to do is I'm going to take my pencil and we're going to go back a couple chapters all the way to chapter 2. And we did a lot of this when two lines are cut by a transversal. We had angle pairs that were formed, such as corresponding alternate interior, alternate exterior, consecutive interior. So we had those angle pairs. And so if you look, before we knew that these lines are parallel, we can see that these two angles right here, they're on the inside of the two lines, on the same side of the transversal. And by definition, those are called consecutive interior angles. And we have this converse thing that says if two angles that are consecutive interior are supplementary, then the lines are parallel. So this, dating way back, that's why we can't forget all these things in math that we've learned this year. This reason is the consecutive interior angle theorem converse. Now, if you can remember, if you start with parallel lines and you want to say that consecutive angles are 180, then you would have the consecutive interior angle theorem. But since we're proving parallel lines, we started with supplementary, it's the converse. Okay? Now, step 3. J is supplementary to M. So what I'm going to do is, here's J, and I'm not going to erase this, but in a different color, let's now mark, they're not congruent, they're supplementary. So now we have these two. So if I take my pencil again, and I think ahead, well, let's see what step 4 says. JK. Well, I'm pretty sure that you can figure out that JK, most likely in this diagram, they're referring to ML. So let's fill that in the blank. Now, why? Well, here we go again. There's angle J is on line JK. Angle M is on line ML. And the transversal that kind of makes a connection is right here. Well, these two angles are between lines that were cut by a transversal. They're on the same side. Well, what do we have? We have consecutive interior angles again. And not only are they consecutive interior, they told us that they add to 180. Therefore, our theorem converse states that if you have two consecutive interior angles that are supplementary, then the lines that form them are parallel. So this is also the consecutive, I'm going to abbreviate now, interior angle theorem converse, just like you wrote in number 4. And then finally, if you think about what we just proved, we said in step 2 that this pair is parallel from step 2. We said that from step 4 we proved that this opposite sides are parallel. So why is it that JKLM is a parallelogram? Well, if you look at your markings, we marked this pair is parallel and this pair. So that means we basically marked that both pairs of opposite sides are parallel. And I've been really stressing this to you. What is that? So our reason, you can simply put, is the definition of a parallelogram. And the definition of a parallelogram is that the definition is that it's a four-sided figure where both pairs of opposite sides are parallel. So you might, if you want to write that down as your answer, that's fine. So I'm going to write both. But remember, the definition is that both pairs of opposite sides are parallel. Okay? Now you are going to be doing proofs in your assignment that goes along with this, so we're going to do one more together. Okay? Now this one is interesting because we are starting with some pretty important given. And what that says, that symbol, is the symbol that you're saying. It is telling you that this is parallelogram ABCD. So it's literally saying to you, hey, we are starting with a parallelogram. So what that means is that, oh my gosh, I could make a list, but here I'm going to say it fast. We know already that opposite sides are equal. Why? Because they told us it's a parallelogram. We know that the diagonals bisect each other. We know that the opposite angles are congruent. We know that the consecutive angles are supplementary. All those things that we've learned about a parallelogram, we already know. So what happens is when it's now saying step 2 is AB, well, we know because it's a parallelogram, the opposite sides are congruent. So I'm hoping that you have DC, and I'm going to mark it as we go. Now, if you're going, well, how am I supposed to know that? What's the reason? Well, if you can remember, once you know something's a parallelogram, one of its properties is that opposite sides are equal. So we're simply going to write the reason for this is that we used a property of parallelograms. Now that's enough, but for your notes right now, you might want to put that property was opposite sides are congruent. So that might kind of help when you look back. Now, it says AB. AB is parallel. Well, I'm thinking it's going to be the side opposite, so it's going to be also DC in this blank. But why is it parallel? Oh my gosh, because we knew from the start, they told us it was a parallelogram. And we know that opposite sides of a parallelogram are always parallel. So that is actually the definition of, if you put property, I would not mark that wrong, but I think you need to really start thinking that the definition of a parallelogram is just a four-sided figure where opposite sides are parallel. Okay? Now, I'm going to use a different color only because I'll stay with purple. It's asking us to look at angle CAB. Well, that's right there. Now, here's the problem. We know that this whole angle is equal to this whole angle by opposite sides of a pair, or opposite angles are congruent. But you see, this is only a piece of it. Now, I'm going to help you here because this is our notes, but I'm going to let you know that the answer is right here. So let's go ahead and fill this in. This is angle DCA. And the reason that CAB is equal to DCA is similar to what we did up above. So here I go. I'm going back to chapter 2. When you have two lines, and in this case, we are starting with parallel lines. Why? Because they told us this is a parallelogram. Cut by a transversal. This angle right here and this angle they are between these two lines that I drew in pencil, and they're on opposite sides. And those are called alternate interior angles. So if you are starting with parallel lines, then alternate interior angles are always equal. And that, for number 4, is the alternate interior angle theorem. It is not the converse this time because we started with parallel lines. Okay, I almost messed up here. So the next part of our proof, and I don't want to show you, but I think you'll get this one pretty easy. If we mark angle AEB, this is congruent to angle what? Well, I'm hoping you remember from our previous chapters, these are just vertical. So this is going to be congruent to angle CED. So that, I'm hoping usually y'all are really good with this one, is the vertical angle congruence theorem. Okay? Now, I didn't really even talk about what we were trying to prove because I know some of this can be a little tricky because it's from previous chapters. But we're trying to prove that two triangles are congruent. And I went ahead and I shaded those two triangles in so you could get a visual of what we're trying to show. And I don't know if you remember this, but from last chapter, chapter 5, right before break, we learned 5 shortcuts on how to show that two triangles are congruent. And I wrote them down here, side, 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 side angle, side, and I think you can remember. So this final reason is going to be one of these. Well, let's look and see what we have. So if we go to our diagram, now that it's all said and done, we have side, angle, angle, side, angle, angle, which is better known as, right, in order, angle, angle, side. So our last reason is angle, angle, side. So I know that's a lot to expect, and that's why I did 2 with you. But please do your best to try those in your homework. Because with worksheet 7.3, you do have a couple proofs that I need you to try and do your best. And you are going to have to think back to previous chapters' theorems and definitions to get those correct. Okay? All right, good job.